Okay, so we're going to take this little bit of the arc over here and work out its effect on the magnetic field over there, and then we're just going to add that up all the way around the circle. Now the effect of a little bit here on there is given by the Biot-Savart law. What does this depend on? It depends on delta L and R. Now delta L is pointing in the minus x direction. How long is it going to be? Well, if the angle changes by delta theta, then the distance along the arc is r times delta theta. That's always the case with circles. If you move an angle theta, your distance along the arc is just r times the angle delta theta, as long as delta theta is measured in radians. So we know that delta L is going to be in the x-coordinates minus r delta theta, 0, 0. How about r? Well, we worked out what r was here. We now know that theta is going to be 90 degrees. So cos theta is going to be 0, sine theta is going to be 1. So that's going to be equals 0 minus r z. And that makes sense because we're dropping from plus r to 0 in y, and we're increasing from 0 to z in z, and we're not changing our x-coordinate. So that all makes sense. Okay, so if we plug this all in, we find that delta B is going to be mu0 over 4 pi. Now we can calculate mod r. It's just going to be square root of r squared plus z squared in this case. So this comes out as I the cross product is going to be 0 z r delta theta r squared delta theta all over r squared plus z squared to the 3 halves. Now all we need is a z component because we've agreed the x and y coordinates are going to add up to 0. So we find that delta bz is equal to mu0 over 4 pi I r squared delta theta all over r squared plus z squared to the 3 halves. Very similar to what we've done before. So we could numerically add them all up. If you want to do that, go ahead. I'm going to jump straight to a calculus solution in this case. What we're going to do, as usual, is if we had big chunks like that long, that long, that long, get an approximate answer. As we make each chunk, each delta theta and delta L smaller and smaller, we're going to need more and more of them. We're going to add up more and more of these things and get a more and more accurate answer. So what we're going to get is that the actual BZ is going to be the limit as delta theta tends to 0 of the sum of the BZs. And as usual, when we take the limit, it turns from a sum into an integral. So that's going to be equal to integral around the entire circle from 0 to 2 pi mu0 over 4 pi by r squared over r squared plus z squared to the 3 halves d theta. Now that's rather an easy integral to do because we're integrating over theta and none of that depends on theta, so that can all just pop out of the integral and we're just integrating d theta from 0 to 2 pi. I hope you can do that. It just comes out as theta from 0 to 2 pi, which is 2 pi. So we find out that the magnetic field in the z direction is equal to mu naught over 4 pi. I'm leaving it written as mu naught over 4 pi because that's how the constant is usually used. It shouldn't be mu naught, it's mu naught over 4 pi. And that's times 2 pi r squared I all over z squared plus r squared to the 3 halves.